So today we're going to continue and finish off the execution-based prefetching that we were about to get started yesterday, and then make a start on multiprocessors. Hopefully this will be fun. I'll make an announcement on the exam time and date and the topics in the middle of the lecture before we transition into 19B. But we will cover more of that next week and the week after. Okay, so let's get started. Recall that we were talking about prefetching, and we've actually covered most of what I wanted to cover. We talked about the 4 questions: what, when, where, and how. And we looked at it from the perspective of software, hardware, and we were just about to start execution-based prefetching. And we talked a lot about prefetching performance, as well as throttling techniques, if you remember. We will touch upon, we will finish execution-based prefetching, which will take some time today. And then we will go into issues in multi-core, but I don't intend to spend a lot of time on issues in multi-core in prefetching. Basically, a lot of the issues that we have seen before are just exacerbated and made worse when you have prefetching agents that inject prefetches into the system. And you need to basically pay special attention to prefetches in multi-core. But that's true for a single core also. You just need to pay even more special attention to prefetch in multi-core. Okay, so just to jog your memory, this is where we left off almost. We talked about content-directed prefetching, and then we talked about making it efficient using hardware-software compiler hardware cooperation in this particular paper. And then we talked about hybrid hardware prefetchers. We said that there are many different access patterns, and different prefetchers are good at covering different access patterns, but they may be bad at covering some other access patterns. As a result, it makes sense to have heterogeneity in hardware prefetching as well, and have different types of hardware prefetchers operating together. Of course, this leads to the downsides of heterogeneity, and you get more complexity, higher bandwidth intensity, and prefetchers start getting in each other's way. So you need to actually control the system. It's like a multi-agent system again, right? You have multiple agents that are injecting prefetches into the system, and you need to be careful about how you manage the system. And if you do that well, like this paper does, for example, then you get even better performance than either of the prefetchers alone. And we discussed some of the prefetchers. Hopefully you find some of the ideas quite interesting and creative. We talked about streaming, striding, linked data structure-based prefetchers, and more localized random type of prefetchers. It's not localized random prefetcher, but the prefetcher is able to cover patterns that have locality, but that do not necessarily have predictability, or at least easy predictability for stride or stream, or multiple stride or multiple stream. Now we're going to talk about execution-based prefetchers, which are actually quite powerful. And in my opinion, they can cover many of the access patterns. But again, they may not be efficient at covering all possible access patterns. For example, the stream prefetcher that we discussed, or stride prefetcher we discussed, is very efficient at covering prefetching for streaming and striding patterns. If you use a Markov prefetcher for streaming and striding patterns, you could cover them. Maybe adjust the you'll miss the compulsory ones, as we discussed, but you will cover them very inefficiently. That's true for execution-based prefetchers also. Execution-based prefetchers, I believe, can cover, well, they can cover streaming and striding patterns, but maybe not so efficiently. And the idea is, I've given you the idea before, but it's a simple idea again, but implementation may be relatively complex depending on how you implement it. Basically, the idea is to pre-execute a piece of the program solely for prefetching data. And it could be a prune piece of program, or it could be a specially created program, piece of program just for prefetching for the main program that you create. And we discussed briefly how to do that. I'm going to go into more detail right now. Basically, if you are doing this for prefetching, you only need to distill pieces of the program that lead to cache misses, and somehow create a thread that discovers these cache misses earlier and brings the data into a shared cache between this prefetching thread and the main program. And then hopefully the main program will get the data from the shared cache and never need to take a cache miss. That's the ideal world, of course. For this to happen, your thread needs to be able to go ahead of the main program and prefetch accurately and cover as many misses as possible clearly. This thread is called a speculative thread. This is the pre-executed program piece. It can be considered a thread. It can be an explicit thread. It can be an implicit thread, as we will see in some of these cases. And speculative thread can be executed in different places on a separate processor or core, just like any other thread, on a separate hardware context, like in fine-grained multithreading or other forms of multithreading, simultaneous coarse-grained multithreading. Or it could be executed on the same thread context in idle cycle. So whenever the main thread is stalled, waiting for memory, for example, you could switch in this speculative thread that's there to just prefetch for the main thread. And we've seen Runahead execution. We're going to go into a little bit more detail into Runahead execution today, but Runahead execution does the last part. But there are examples of Runahead execution that can be executed on a separate hardware thread context. For example, the Runahead execution implementation in IBM Power 6 is done on a separate hardware thread context. As a result, it has some overheads as well as potential benefits as well. Okay, clearly, if you do it on a separate processor or core, you need to still share some caches so that you can get some benefit between the main threads processor and the speculative thread processor. So there are clearly advantages and disadvantages to executing the speculative thread in different respective places, right? For example, if you execute the speculative thread on the same thread context, you need to save the context of the main thread somewhere, meaning checkpoint its architectural state, and also flush its pipeline probably, right? As we had seen in Runahead execution. And we will see more in this. So that's one place, basically. Where do you execute the speculative thread? This is one of the questions of where that comes into play with execution-based prefetchers. And then there's how to construct the speculative thread, which is perhaps even more interesting. Although all of these are interesting, and you need to do all of these well if you want to get the prefetcher right. But how is clearly very important because you need to construct this thread, and that how you construct this thread determines your coverage, accuracy, etc. And as I mentioned earlier, you could do it in a software-based, hardware-based, or in some cooperative manner. When I say pruning over here, you need to somehow prune the main program such that you distill the pieces that lead to these cache missing instructions. And you need to add some spawn or fork instruction that forks the speculative thread early enough, such that the speculative thread makes enough progress and prefetches early enough for the main thread. You can do exactly the same things in hardware, basically. The difference between software and hardware is in software, clearly the compiler or the programmer does this. In hardware, it's done transparently, so there's some hardware cost to do it. And literature has both of those techniques that are discussed on how to construct a speculative thread. For example, there are works at Intel that discuss dynamic speculative precomputation that do both software and hardware-based pruning as well as spawning. A separate form of this is you can use the original program without constructing the speculative thread. This makes life easier a little bit, but execute it faster without stalling and correctness constraints. So this is exactly what Runahead execution does, for example. As a result, it's an execution-based prefetcher that doesn't need to prune the program, as you have seen and as we will see more. So you could actually do many, many things here. And there's a lot of interesting ideas that have been proposed, but clearly we cannot go into all of those ideas. So speculative thread, let's talk about how you actually need to generate the speculative thread. First of all, speculative thread needs to discover cache misses before the main program reaches them. Clearly, otherwise it will not be prefetching well. So it has all the properties of a prefetcher. It needs to be timely. It needs to be hopefully high coverage and high accuracy, right? So to be able to discover misses before the main program gets to them, you need to avoid waiting or stalling, or you need to compute less, meaning you need to be very stringent in terms of what you execute in the speculative thread. And to get ahead even further, speculative thread probably needs to perform only address generation computation, maybe branch prediction to guide where you need to go, of course, because if you actually go on a program path that's not going to be executed by the main thread, then you'd be prefetching useless stuff probably, right? Potentially, not always, because sometimes wrong path is good for prefetching, as we will very, very briefly discuss as well. But all else being equal, it's better to have the speculative thread to follow the same path, same program path that the main thread is going to follow. And to be able to do that, you need to be careful. You may need to do branch prediction in the speculative thread. And you may actually need to do value prediction also, because you need to start the speculative thread somewhere. And that's somewhere maybe a place where the main program did not reach yet, because you need to do the speculation far ahead from the main program, such that the main program doesn't get to the load instructions that are executed by the speculative thread before the speculative thread executes them and finishes them, right? Clearly. So some values for the speculative thread, input values for the speculative thread's execution may not be available yet. They may be unknown. Or you may not even know that they're unknown at some point, right? Depending on how you construct the speculative thread. So you need to actually do some potential value prediction for those instructions that don't have values as inputs to the speculative thread. So there's actually a lot of interesting design choices that you can make in constructing the speculative thread. And the key thing is the speculative thread is purely speculative, meaning it's just like a prefetching thread, right? It's not updating the architectural state for the main program. It may update its own architectural state, but it's going to discard that architectural state in the end. It's not going to have any effect on the programmer themselves or any other software. The goal is purely prefetching. And there's no need for the recovery of the main program if speculative thread is incorrect. Incorrect meaning if it goes down a wrong path, if it prefetches something useless, if it generates a segmentation fault. I mean, you don't even need to generate segmentation faults, for example, and or exceptions in the speculative thread. And eventually, basically, you kill the speculative thread if you figure out that it's not doing something useful, or if it's off the weeds, meaning that it's generating all of these faults that you're not really raising to handle. So it's purely speculative, basically, and it makes sense. This gives a lot of freedom to the designer of the speculative thread or creator of the speculative thread to optimize it for pure prefetching purposes. Okay, so let me give you some examples of what can you do. Thread-based pre-execution is actually a very general idea. You don't have to do it just for prefetching. You can actually do it for predicting the branch outcomes earlier. So the idea was first proposed in, I believe, these two papers. One of them is a technical report. It's called Assisted Execution. The other is called Simultaneous Subordinate Microthreading. Interesting names, clearly. Basically, the goal of these speculative threads is to assist the execution of the main program. They're basically acting as service threads that provide some prediction, for example, for the branch that is hard to predict, or for the load that keeps missing in the cache and the prefetchers may not be working well for them, right? So you can see this is a nice picture, and this picture is actually taken from this last paper, which is a nice paper, which I will briefly discuss later on. It's called Execution-Based Prediction Using Speculative Slices. But basically, you identify the problem instructions, let's say, branches or loads in the general form of the idea. And then you somehow form a thread that would prefetch the load or predict the outcome of the branch, meaning you find instructions that lead to the load address and that lead to the branch outcome. And you basically execute only those instructions. There may be other instructions in the program that you don't want to execute because they have nothing to do with this load, right? Or they have nothing to do with this branch. And you execute only those instructions, and you potentially execute the instructions that lead to this load clearly. And basically, you create a thread that does that execution, and you put the fork point early enough such that the thread executes and the cache miss gets handled before the load instruction is executed by the main thread. That's the idea, basically. And you do a similar thing for branches. In fact, the simultaneous subordinate microthreading paper gives an example from the branches. Their goal was to really improve the branch prediction accuracy for hard to predict branches. And they constructed these speculative threads to pre-execute the branches and the code data flow that's leading to those branches. And they forked the thread early enough such that the prediction is available just before or enough before the branch is actually fetched by the program. So there's a question: how does forking work in hardware? That's a good question. It depends on how you design it. Basically, you can basically create a context. Again, there's a lot of freedom for the designer over here. You could fork in hardware. You could fork in software. It's very similar to forking in software, but maybe the overheads are much lower. Basically, you can initialize the registers depending on what you think the registers should be. So basically, forking at the very basics you need to have a separate thread context to execute. And then you need to fill up the registers that you need, architectural registers that you need, and you need to fill up the program counter that you need. And you probably need to fill up the virtual memory or memory management unit registers that are architectural. And you use the main threads registers for that, but some of the registers may be different actually, as we will discuss later on. Okay, so it's very similar. The takeaway is it's very similar to how you do it in software, except it's much lower latency. And you don't need to do everything that you do it in software because this is purely speculative. Keep that in mind. Okay, so hopefully this is clear. You can do this on any problem instruction, let's say. It could be some problem critical computation that you have also that doesn't have branches and loads. But in general, in computer architecture, the most problematic instructions tend to be branches and loads. Because they're hard to predict in general. Okay. So there are multiple issues in thread-based pre-execution. I'm going to talk about them. Where to execute the pre-computation thread, when to spawn the pre-computation thread, and when to terminate the pre-computation thread. So we've already discussed these. There are clearly trade-offs associated with them. I'm not going to go into the details, but very quickly, if you execute the pre-computation thread on a separate core, you have the least contention for hardware resources with the main thread because they're not concurrently executing on the same pipeline. But you also have the least sharing of the caches. As a result, you may not hide the full miss penalty of an L1 cache miss, for example, maybe not even an L2 cache miss. If the shared level is L3 cache, you prefetch into the L2 cache. You can execute the pre-computation thread on a separate context on the same core in simultaneous multi-threading, fine-grained multi-threading. Clearly, this leads to more contention. So you may actually delay the main thread while executing the pre-computation thread, but you actually have tighter sharing of the caches also. You could do it on the same core, same context, and when the main thread is stalled. Here, you actually may or may not have contention because main thread is stalled, it's not executing, but you're flushing its pipeline potentially. So you actually have some overhead on the main thread, and you're polluting the caches potentially if you're on the wrong path in all of these cases actually. But this is actually taking advantage of the idle cycle. So I think this number 3 is a clever idea. But the downside in number 3 is whenever the main thread is not stalled, you do not execute. As a result, you have limited time for prefetching. In a sense, your prefetching distance is limited. Keep that in mind. So prefetching distance and degree also apply to thread-based pre-execution if you imagine it's right in the right way. When to spawn the pre-computation thread, this is very important. You insert the spawn instructions well before the problem load, you would like to ideally. The question is how far ahead. So you run into similar issues like prefetch instructions in this case, but here you need to be more careful because you're going to execute a thread. It's not just a single instruction. If you put the spawn instruction or fork instruction or do the hardware forking too early, then prefetch might not be needed, right? Because you may actually, the main program may go to a different path, just like with a prefetch instruction. If you do it too late, prefetch might not be timely. So this is, again, an important calculation that you need to do. And there are works that describe how to do this in literature. Or you could do this when the main thread is stalled, which is another approach. Clearly, you execute the pre-computation threads. Regardless of however you construct the main pre-computation thread when the main thread is stalled, then this is actually an interesting option also. But again, here you're limited by the prefetch distance. And the last one is when to terminate the pre-computation thread. This is an interesting issue. So you can have pre-inserted cancel instructions in the main thread, or you can have pre-execution stop instructions, as we will see in the pre-computation thread. So pre-computation thread may be pre-computing, and when it reaches a pre-execution stop instruction, it basically terminates itself. Or you could have somebody monitoring the effectiveness or contention that's happening, just like we did in feedback-directed prefetcher throttling in hardware. You could do this in hardware, you could do this in software, and basically you can throttle the pre-computation thread or kill it essentially or terminate it. Right? So there are many things, a lot of things that we discussed can be applied at a high level to pre-computation threads as well. So let me quickly go over a paper that discusses a lot of interesting issues in pre-execution. And this was published in ISCA 2001. You can read the title, Tolerating Memory Latency Through Software-Controlled Pre-Execution in Simultaneous Multi-Threading Processors. And I like this paper a lot because it really is comprehensive. It discusses what, when, where, and how of thread-based pre-execution. And it gives a lot of good examples that look like this. So it's good to look at these examples. So the author says there are different places where pre-execution can be launched and they could benefit. So I actually mentioned this yesterday. You may have multiple pointer chains that you're going through. For example, you may have multiple hash table lookups, right? Hash table lookup 1 does a linked list traversal in one bucket of the hash table. Hash table lookup 2 does another linked list traversal. Hash table lookup 3 does another linked list traversal, etc. But the main thread can only do one of the traversals at a given time, right? So while the main thread is working on this traversal, you may launch a pre-execution thread that does the hash table lookup on the next bucket, or whatever the input tells you which bucket it would be. And this thread can be going in parallel, speculatively, of course. You can see that pre-execution in this thread, while this main thread is chugging along and doing its work. And you could actually launch multiple pre-execution threads, as this paper shows. You can, in this case, the paper shows that you have 3 pre-execution threads operating on 3 different pointer chains, while the main thread is operating on the, let's say, architectural pointer chain. I just abused the word architectural over there, but main thread, eventually the results will be visible to the software, whereas these results will not be visible. They will just prefetch these nodes that they're touching into the caches. That's the idea. And this paper discussed other options like non-affine array accesses. You can read the paper. Again, you can have multiple arrays you're traversing. Only one of them can be accessed potentially by the main execution because you're doing sparse array accesses in this particular case. But other, you can start the array accesses to other arrays in a pre-execution thread or multiple different pre-execution threads. That way you prefetch the things that you touch in the other arrays into your caches. Or you could do multiple procedure calls. You can see that there are 4 procedure calls the program will consecutively reach, but main program operates on one procedure call at a given time. But you can launch pre-execution threads that operate on the 3 procedure calls that you expect the program to reach at some point, right? And you can see that these are pre-executed concurrently with the main thread. Now, of course, this is a good example to see maybe you don't know some of the input values to this bar call, right? Or these different function calls. So what do you do to pre-execute these threads? Maybe you predict the value of a register, for example, because you don't know, maybe foo will write a register that will be input to bar. You don't know exactly what that register value is. Maybe that register value is not important for prefetching purposes. You can figure that out with software analysis clearly. If it's not important, that's great. If it's important, maybe you do a value prediction and still do pre-execution, right? So that sounds cool. So you have a lot of freedom to actually construct these pre-execution threads. But if you do it wrong, this is pure overhead also, because remember that this paper is executed on simultaneous multi-threading processors. While the main thread is running, another thread is concurrently executing in the same processor in a separate thread context. So you need to be really careful in terms of what you put into the speculative threads. If you're doing useless work, you're really taking up execution cycles potentially from the main thread, or maybe some other accurate pre-execution threads. And the last one over here is you can see that main thread is working on this part of the control flow. Maybe you speculatively pre-execute different paths in the control flow, right? And this is a tougher thing to do, of course, but you could potentially do that, right? You could say, I don't know if this branch is going to be predicted. Basically, I think that this branch is very hard to predict. 50% of the time I will predict this way, 50% of the time I will predict this way. And that's true for this branch also potentially. So what I'm going to do is, at this point, I'm going to launch pre-execution threads from here, and from here. And they will just be pre-executing the program for prefetching purposes. And if I actually go this way, hopefully I will have the data in my caches. If I actually go this way, hopefully I will have the data in my caches, right? By the time I get there in the main thread. So this is a very powerful idea you can see. And again, this is not dependent on what kind of pattern you have. This can potentially prefetch any pattern. Clearly linked list traversals. All you need is parallelism in your linked list, or you need to be able to create parallelism in different linked lists, as you can see is done over here. Okay, so let me give you an example from this paper. This actually, you can read the paper for more detail also, but I like this example. Basically, this paper shows that this is an example from a vehicle scheduling program that's in Spec 2000 benchmark suite. It's called MCF. And basically, this paper shows an abstract version of a very important part of the program, which leads to half of the execution time of the program, which is a double loop. You can see that there's a for loop and there's a while loop internally. So this is the inner loop. Basically, the paper shows that you can pre-execute the while loop for the next iteration of the for loop. Basically, while the main thread is operating on one iteration of this for loop, we'll launch a pre-execution thread for the next iteration of the for loop, which that pre-execution thread, what the pre-execution thread will do is it'll essentially execute the next while loop completely and hopefully prefetch the data that is touched by that while loop. And when the main thread comes to the next iteration of the for loop, hopefully all of the data over here is already prefetched. That's the idea, basically. And how does it do that? Basically, this relies on software or programmer or compiler inserted instructions. One is a pre-execute start instruction. And you can see that there are comments over here. You invoke a pre-execution starting at end4, and end4 is over here. Basically, the main thread is executing over here. It gets to a pre-execution start instruction, end4. It basically forks a thread, a speculative thread, that does pre-execution starting from the end of the while loop, end of the inner loop, basically, which means that you set the next iteration of the loop, the target address of the pre-execution. You can see that I++ and rcount +3, which is needed for the next iteration. And then you go to the next iteration, and then you do all of this. And then basically, while the pre-execution thread is executing over here, it ignores the pre-execute start. That's the design choice that the author made over here. It says basically we don't want to do nested pre-executions. A pre-execution thread cannot start a pre-execution. This is a design choice. It can in other design choices, but if you don't have enough thread context, this is probably a reasonable design choice. And basically, the pre-execution thread ignores the pre-execute start, but it doesn't ignore all of this. So it keeps executing this while loop in the second iteration. And when it gets to a pre-execute stop, it terminates itself. That's the idea. And while it is executing this part, the main thread is probably executing this part in the previous iteration. So what we're doing over here is while main thread is executing an inner loop in one iteration, we're really overlapping that execution with a pre-execution thread that's speculatively executing the inner loop of the second iteration. And if the pre-execution thread is correct, which is the case here, actually, this is an easy case because you can see that pre-execution thread, what should I say? The pre-execution thread doesn't need input values, let's say, from this inner loop that needs to be executed by the main thread. So there's no dependence between the main thread and the pre-execution thread, which is a good thing in this case. That way pre-execution thread can correctly execute. The only case where pre-execution thread will not be useful is when you're at the end of the iterations of the for loop. So you actually start a pre-execution for the next iteration and the next iteration doesn't exist. In this case, you also correctly figure that out. Basically, you go to pre-execute stop over here because you basically check whether you need to execute the for loop. And then if you don't need to execute the for loop, you fall out and you terminate the pre-execution if you already passed the end of the for loop. There's another pre-execute stop over here, as you can see. So this is purely software controlled pre-execution, as you can see. Of course, this requires hardware instructions to be able to fork and help with all of these instructions. And I will talk about those instructions next. So basically, these are the ISA extensions that are needed as seen by the programmer, let's say. Clearly, ISA will have some other encoding that's not described, but you can see that this paper uses C syntax to improve readability. So there's pre-execute start, which requests for an idle context to start pre-execution at start PC, and it stops with max instructions, assuming you provide a max instructions value. So you can actually control the pre-execution by saying you will execute at most 1,000 instructions, let's say. I just made it up. Thread ID holds either the identity of the pre-execution thread or -1 if there's no idle context, so you need to account for that clearly. This instruction has effect only if it's executed by the main thread. So basically, the design in this paper disallows pre-execution threads to start pre-execution threads. As I said, that's a design choice. You may not want to do that sometimes. You may want to go deeper in the pre-execution chain so that you can prefetch ahead. That way you can increase coverage, increase timeliness, potentially degrade your accuracy, and potentially cause more contention, clearly, right? So pre-execute stop, as we discussed, the thread that executes this instruction will be self-terminated if it's a pre-execution thread. If it's the main thread, there's no effect, clearly. And pre-execute cancel with a thread ID means that you terminate the pre-execution thread with the thread ID. So main thread can actually do this also. And you may think about where you want to do this. If the main thread for some reason thinks that there's no need for pre-execution at this point, it may cancel the pre-execution threads. You can certainly add other instructions like throttling instructions, but this paper doesn't do that, and I'm not going to talk about that. But let me give you the performance results that this paper shows on some difficult applications like MCF, minimum spanning tree, that we discussed last time. Actually, there are a lot of linked list based. These two are very linked list based programs. And you can see that in many cases, there's a significant reduction in execution time. And this is by using a separate thread context in an SMT processor. Not in all cases, though. In this case, for example, the execution time increases, and there's a discussion in the paper. You can see that. There's resource contention that happens between the main thread and pre-execution threads over here, and that leads to increased execution time. And also, you can see that this program doesn't necessarily have a lot of cache misses. It's very compute bound. So you need to be careful, basically. But the memory bound programs see significant benefits, as you can see, 24% in this case, 27%, 36% in this case. Okay, so hopefully this is interesting. And these are results on real systems. Let's talk about these problem instructions a little bit more. These are the two papers that discuss, I believe, problem instructions in a nice way. Basically, these folks have analyzed what they call the backwards slices of performance degrading or problem instructions. They basically analyzed a bunch of interesting programs that are hard to parallelize. The virtual place on route is one example. This is a routine from that program that basically looks at two problem instructions. You have a cache miss, you have frequent cache misses in this instruction, and you have frequent branch mispredictions in this instruction. These folks analyze the backward slice of a lot of these instructions, and they discuss how to construct these pre-execution threads, if you will. I'm going to go through this relatively quickly. If you're really interested, you can read how things are done in the paper. But I believe in these papers, they did it manually as opposed to doing it automatically. But a compiler can potentially do what they describe as well. But basically, the first step is really identifying what are the problem instructions, problem cache misses, problem branch branches. And then you need to potentially figure out where to put a fork point. You have to do this, I think, after you construct a thread. But just to give this high-level picture, this is the instruction add to heap. You're adding something to a heap, basically. It's a heap insertion routine. And that is called by a higher level function, node to heap. It does something. And then you may put the fork point from that function, and early enough, as you can see, somewhere over here, basically. But that requires some calculation to decide what's a good place to put the fork point, clearly. It's very similar to what we discussed with prefetch instructions, except you're not just going to execute a prefetch instruction here. You're going to execute a full thread concurrently with the main thread. Well, full thread meaning a speculative thread that you should prune as much as possible. So for those problem instructions, you can see this is the alpha assembly for the add to heap function. And the instructions that are problematic are annotated. So these are the bold instructions. So this is the branch instruction that's problematic. This is the load instruction that keeps missing. Now, I think the problem instructions, the shaded instructions comprise an unoptimized slice. What does this mean? Basically, the shaded instructions are somehow the instructions that you need to execute without optimization to actually calculate the data values that lead to, basically to actually compute these problem instructions, the branch and the load. And clearly there are some later instructions that lead to, because there's a loop here that you need to loop, because some of the instructions, some of the load values as well as branch directions are dependent on the prior iterations of the loop, clearly. If you don't optimize the slides, basically you need to execute a lot of instructions. That's the takeaway over here. Almost the entire program, as you can see. Only the non-shaded instructions don't need to be executed. But you don't want to execute the entire program, as we discussed, right? If you execute almost the entire program, this pre-execution thread cannot be necessarily effective, right? So you really need to aggressively prune the slice. And these folks prune the slice, and you can see that the final slice for both of these instructions is much smaller than the original code. And the slice actually contains a loop that mimics the loop in the original code. So they don't exactly do the original code. Basically, they convert the conditional branch over here, branch greater than, to an unconditional branch, as you can see. Basically, they say that we're not going to do branch prediction for this particular thing because we expect this loop to execute many times. And unconditional branches are clearly easier to execute, and you don't need to do the branch computation, the computation that leads to the branch direction if you have an unconditional branch clearly, right? Because there's no computation that you need to do. The branch is directly jumping to the sliced loop location without any data flow that's leading to it, right? Okay, so you can see that's one way of eliminating computations that really do not need to be done by the pre-execution thread. And there are other ways, which I'm not going to discuss. You can read the paper. But basically, you can have a thread with this many instructions, and that's it. While the main thread is executing, I don't know how many instructions, but at least this many instructions here. But I think they skip some instructions also. You can see skips 40 instructions, etc. So they don't even show all of the instructions over here. So while the main thread is executing, I don't know, 80 instructions, you're executing 8 instructions over here. That's why the pre-execution thread can go much faster and discover these problem instructions much earlier. So hopefully that's clear. If you're interested, I would recommend reading these 2 papers along with the previous paper that I mentioned. And these may be part of the bonus readings as well. Okay, feel free to ask any questions if you have. I think this is a fascinating topic, and there are clearly a lot of design choices. We've seen Runahead execution before, and Runahead execution is also an execution-based prefetcher. So I'm going to go into a little bit more detail into Runahead execution for various reasons. One is it's one of the simplest execution-based prefetchers that are out there. It's purely hardware-based, and it's quite effective. But it also displays all of the interesting characteristics of an execution-based prefetcher. It answers the questions what, when, where, and how in clearly some ways than others. And I'm going to talk about this because the other reason I'm going to talk about this is because my PhD thesis, and I'm excited about it. And I would recommend everyone to do a PhD thesis that they're excited about even 15 years after they've done the PhD thesis. Okay, there's some question over here. Tim asks, doesn't this consume a lot of extra power? Is this using a mobile phone? So the first question is, yes, potentially. In fact, there are works that cover the power consumption. I'm going to talk about it within the context of Runahead execution as well. So if you do it, if you execute a lot of instructions, you will consume a lot of power, no question about that. If you execute few instructions, you will consume some power, but hopefully the benefit you get from that additional power outweighs the overhead of the power that you add, because you will execute the program faster, right? That way you can save energy potentially, right? So that's absolutely true. Is this using a mobile phone? That I cannot answer that question fully. So we don't exactly know what different companies are potentially doing. It may or may not be. So that's a good question. Unfortunately, companies don't tell much, but potentially they could be, right? If they find a simple way of doing things. I think these are techniques that can potentially lead to high performance. Also energy efficiency. You could make it energy efficient, actually, as I will show you with Runahead execution. And not a lot of complexity potentially, right? Because you already have a lot of the infrastructure to do thread forking, etc. in your system. So hopefully that answers your question. We'll get back to the power issue in a little bit. Okay, so let's talk about Runahead execution. Actually, we talked about this briefly, but I'm going to treat it in a little bit more detail in this lecture. Basically, Runahead execution is a simple pre-execution method for prefetching purposes. And we already talked about the idea. I didn't cover the slide, but let me give you the idea again. When the oldest instruction in the processor is a long latency cache miss, the processor checkpoints the architectural state, which is the architectural registers and the program counter, and enters Runahead mode. In Runahead mode, the execution is purely speculative. You keep executing instructions. The sole purpose is to generate prefetches, and instructions that take a long time, whom you don't have the values for, whom you don't want to handle, like TLB misses or page faults, etc. You just drop them. Basically, because this is purely speculative, you can do whatever you want, right? You're not going to give the results to anyone later on. Your sole purpose in this is pre-execution to generate prefetches. And you mark the results of these instructions invalid, saying that this is a bogus value, don't trust it. And you drop these instructions. And later instructions that source these invalid values can also be dropped, basically. And Runahead mode ends when the original miss returns. And at that point, the checkpoint is restored and normal execution resumes. Basically, you restore the architectural state of the registers and the program counter, and you basically continue as if nothing happened. Right? That's the idea. But hopefully something happened. And that something is, while you're in Runahead mode, you generated some miss that you couldn't have reached otherwise if you stalled. And you parallelized those cache misses, one you're waiting for and the miss that you actually reached. And then when you go back to the main execution mode, let's say main thread in this case, in thread-based execution terminology, when you go back to the main thread doesn't see that miss. As a result, you save a bunch of cycles. And this could be energy efficient as well because you're saving potentially a lot of cycles in the end, right? That's the idea, basically. So I've given you this picture before, basically. If you have a small window, at some point you stall. And if you stall and do nothing, you don't get to the next miss. Whereas Runahead mode doesn't stall. It pre-executes the program. It enables you to get to the next miss and enables the processor to service those misses in parallel. And if you're lucky, or if you're careful, or both, when the main thread, when you go back to the non-speculative execution in the main thread, you save a bunch of cycles. And we're going to go into a little bit more detail in this one. So there are actually more than prefetching benefits. Basically, instead of stalling during a long latency cache miss, so in this, when we did the work, we did it on an L2 cache miss, but we examined on L1 cache miss, etc. If you read my dissertation, you see a lot of design choices examined actually. But during a long latency cache miss, you pre-execute load and store instructions speculatively. And the ones that are independent of L2 miss instructions generate very accurate data prefetches. Why very accurate? Because you're really following the program path that the program would otherwise follow, hopefully, directed by the branch predictor. For both regular and irregular access patterns, actually. Instructions on the predicted program path are also prefetched into the instruction or trace cache and the L2 cache. So there's actually benefit from instruction prefetching. There's also another benefit. You actually, if you have a hardware prefetcher already, you train the tables using future access information. So now your prefetcher can be trained and run ahead as well. And your branch predictor tables can be trained. Of course, you need to be a little bit careful to not confuse your prefetcher as well, which I'm not going to talk about. You can read the papers and my dissertation for detail on this if you're really interested. Let me go into a little bit more detail into the Runahead execution mechanism. Basically, this is an execution-based prefetching mechanism, as I said. Whenever the thread, oldest instructions in a cache miss, long latency cache miss, the main thread checkpoints its architectural register state in hardware, completely in hardware. We do this checkpointing. And then you enter into a speculative processing mode that's specially marked with a bit in hardware saying that you're in the speculative processing mode. I'm going to talk about instruction processing in Runahead mode because entry and exit are probably easy to imagine. When you're exiting, you just need to restore the architectural state from the checkpoint, meaning you have saved the register somewhere, you just restore them back. You have saved the program counter somewhere, you just restore them back. And you don't need to checkpoint everything. For example, memory. Clearly, it doesn't make sense to checkpoint memory because memory could be huge. But because the execution is purely speculative in Runahead mode, you don't update the memory locations. That's the idea over here. You may update them in a speculative buffer, but you don't update the architecturally visible memory locations. That's true for speculative threads as well. Speculative threads may work on their own memory locations, but they cannot update the memory locations that are architecturally visible to the main thread or some other software. Makes sense, hopefully, right? Because these are purely speculative. So you don't need to checkpoint everything clearly. You just need to checkpoint some things that you really need to checkpoint, architectural register state and the program counter clearly, so that you can execute this instruction in the same thread context that the main thread is executing. So let's talk about instruction processing in Runahead mode. So basically, Runahead mode instruction processing is exactly the same as normal instruction processing, just like in main thread, except it's purely speculative, as I said. Architectural or software visible register and memory state is not updated in Runahead mode. L2 miss and also L2 miss instructions and L2 miss dependent instructions are identified and treated specially. They're quickly removed from the instruction window and their results are not trusted. clearly, because you don't have the value. You haven't finished the instruction in the main memory or wherever the next level of cache, and the instruction's value did not arrive. The destination register is not valid, so they're marked as invalid. Basically, that's what this slide is talking about. Basically, so this enables the Runahead mode to go much faster than the main thread. Basically, you're ignoring some instructions, right? Some instructions that are otherwise going to take longer, you say, this is going to take too long. I cannot wait for it. And it doesn't make sense for me to wait for it because it's going to come back 500 cycles later. So I'm going to say, I'm going to launch the request and I'm going to declare my destination register invalid. And anybody that sources that destination register is also going to see that the register is invalid and they're going to mark their destination register is invalid. Okay, so hopefully that's clear. This happens in L2 dependent instructions, for example, but it's not limited to that. L2 dependent instructions are clearly interesting because they're low latency. So there are two types of results produced in Runahead mode, invalid and valid. Invalid means it's dependent on L2 but more broadly, it means that I don't have the value, I don't have time to generate it, so I'm going to mark it as bogus. You can do it with any instruction that takes long. For example, a floating point instruction, floating point divide. Your purpose is prefetching, right, in Runahead mode, or in a speculative thread. Does it really make sense to execute a floating point divide instruction? And usually the answer is no. Why? Because the result of a floating point divide instruction, you're not going to generate an address with it. I have not seen a program that generates an address with it. But of course, programmers do weird things. You could cast it into an integer and then generate an address with it, but usually that doesn't happen. That's a terrible program, probably. If the result of a floating point instruction may affect the address of a load instruction by affecting the control path that's executed, because you may branch on the result on the floating point instruction, clearly floating point divide instruction, but that's also not very often that happens. So you could say, as a designer, I'm not going to execute floating point instructions in Runahead mode, and all of the results are going to be marked as invalid. And actually, we did that in one of the works, and that improved the efficiency of Runahead execution significantly, for example. So invalid, while the original definition was it's dependent on L2 it means that this result is not to be trusted. Okay. And these invalid results are marked using invalid bits in the register file and the store buffer, and maybe the cache itself. I'm not going to go into the details of this a lot, but basically you need to keep track of these invalid values so that you don't trust them. Now, that said, if you don't keep track of them perfectly, it's also fine, because in the end, you're not updating architectural register state, right? So there's a lot of freedom and slack that you're cutting yourself by being purely speculative in the speculative thread. Of course, updating them enables you to do better predictions for the load addresses that are coming later on, right? Invalid values are not used for prefetching and branch resolution for the reasons that we don't trust them, basically. Because if it's an invalid value, the value is not to be trusted. The value is not really correct. It may be correct, actually, but you don't know it. And as a result, we basically say we're not going to use them for prefetching and branch resolution, because that may actually put us the wrong path, or that may actually lead to inaccurate prefetches. Another option is, as opposed to calling things invalid, you can predict the value, right? You can say, okay, the value is 0, the value is based on some prediction, and that actually has some benefits that I'm not going to talk about a lot, but in the enhancements, we will discuss that a little bit. Okay, so the key thing in the speculative execution mode is to remove the instructions from window. And if the instructions, basically the key principle here is, if the instruction is not going to be beneficial for prefetching purposes, get rid of it as soon as possible, because your goal is to really prefetch, right? To simplify things in a processor, we remove instructions in the age order still. Oldest instructions examined for what's called pseudo retirement. An invalid instruction is removed from the window immediately. A valid instruction is removed when it completes execution, because some of the valid instructions may actually lead to cache misses, right? And at that point, they become invalid, or they may be part of a dependence change that leads to a cache miss. So you really want to execute some valid instructions that lead to dependence chains that are part of the dependence chains that lead to cache misses. So the key thing is, if you pseudo retire, we don't call this retirement because it's completely speculative, right? Retirement implies that it's not speculative. You update the architectural state. We're not doing that. So these pseudo-retired instructions free their allocated resources, and this allows the processing of later instructions. That's the key thing. You don't want to increase the resources. You basically want to use exactly the same resources that we have in a processor for this pre-processing. And pseudo-retired stores communicate their data to dependent loads. I'm going to talk about this briefly, but I see that there's some question. How do we communicate the L2 misses in Runahead mode for fetching? I don't quite understand the question, I think. But basically, if you get an L2 miss in Runahead mode, what happens is you generate a prefetch request into the memory system, and the instruction writes its destination register and marks it invalid. Its destination register is garbage, essentially, and the instruction gets removed out of the window when it becomes the oldest. So basically, you just generate a prefetch request into the memory system for that instruction. Hopefully that makes sense. Okay, so the difficult part, the most difficult part in Runahead mode is store load handling, because clearly we cannot update memory, right, with stores because we're not updating things architecturally. But there may be some load instructions that want or that source the data values that are written by a store that's executed speculatively in Runahead mode. Right? This is called the pseudo-retired store. So for this purpose, or store load communication, we have special structures, a special structure called the Runahead cache. This could be implemented in multiple different ways. If you read my dissertation, actually, you will see several different ways over there. But basically, the whole purpose is data communication through memory in Runahead mode. So a pseudo-retired store writes its data and invalid status to a dedicated memory called Runahead cache, and a dependent load reads its data from this Runahead cache. This is purely speculative. And the reason is because we cannot write to memory. You cannot write to memory because if you write to memory, you're updating architectural state. We're basically writing to a buffer. It could actually be called the Runahead buffer. We call it the Runahead cache because it looks like a cache structure. And again, this doesn't need to be always correct. Size of Runahead cache can be very small. Why doesn't it need to be always correct? Okay, you get a store instruction. Maybe because you don't have enough space in this Runahead cache, a load instruction gets a wrong value. It gets a stale value in the memory location. What happens? Well, in the worst case, you'll miss. In the worst case, you'll generate a bad prefetch, right? That will not be used by anyone. And clearly, that's the inaccuracy of your prefetcher. And this doesn't happen very often, as I will show you as I may show you later in one of the slides. But this is one of the most complicated parts of the Runahead mode store load handling. Okay, branch handling is a bit easier, but if you have a branch that's invalid, one of its inputs is invalid, that means that you cannot resolve the branch, right? This is interesting. Now we rely on the branch predictor when we're executing in Runahead mode. But if it's a valid branch, we can resolve it and we can initiate recovery if the valid branch is mispredicted because we trust the data value, input value of the valid branch. But if it's an invalid branch, it's not a problem if it's predicted correctly. But we don't know if it's predicted correctly because we cannot execute this branch or we cannot trust the execution of the branch, right? Because we don't have the input values correct. If it turns out to be a mispredicted invalid branch, the processor cannot recover from that branch. So you're always on the wrong path after that until the end of the Runahead execution. And this becomes interesting because you may execute for a long time in the wrong path. And I did a lot of analysis of what happens in the wrong path when you're in Runahead mode. And usually wrong path is useful, but it's not as useful as you being on the correct path. So if you're given a choice, choose to be on the correct path. Let me put it that way. But of course, you don't have a choice over here. How do you know that you mispredicted the branch when you cannot trust one of the data values, right? One of the data input values. Okay, so there are a lot of interesting issues, clearly. But the fact that you're purely speculative eases all of these issues. All of these issues exist in an out-of-order processor or even an in-order processor as well. But you need to handle them perfectly correctly because your purpose is really to execute the program in main thread or in non-speculative mode. But Runahead mode is purely speculative, so you can actually design the system to execute in a purely speculative way and give up correctness because you don't affect correctness in the end, right? Okay, let me see one. Can you elaborate on how mispredicted invariant branches are still useful? So let's actually defer that discussion because I have one slide that talks about wrong path events later on. But okay, let me give you one easy point. Let's assume that you have a branch, if then else branch, right? You have a fork. You have an if then else. So you have two parts that you need to take. And then they go back and they reconverge at some point. Actually, I will, maybe I will use, actually, maybe I will use my thing. What is this thing called? iPad, yes, thank you. So if you could give me a couple of minutes, I will talk about it since you asked. And this is probably an okay point to talk about because I don't intend to talk about it much, but I will point you to multiple papers related to this. Now, Jisung is going to give me rights to present because I cannot figure out myself how to do that for some reason. And he's going to do it for the new Onur Mutlu who enters, but I cannot enter because I need a passcode. I don't know why this passcode is not automatically copied. Okay. Okay, now I did enter. Can I present? Okay, I cannot share. Is somebody over there that can help me share?
I think you can share now, Onur, just make you a co-host.
Okay, thanks. Okay, yeah, I can share. Thanks, Geraldo. Okay, start sharing. I don't know why. Okay, it's asking me to stop sharing on the other screen. Okay, so let's do it this way. This is going to be relatively quick, I think, assuming I have battery on my stylus. So basically, let's take a look at this. These are basic blocks. You have a branch, and you have some block you execute here, some block you execute. Let's make them asymmetric, doesn't matter. And then, so this is the control flow graph of the program, right? And this is a branch, this is an if iteration, and this is the then part, and this is the else part, let's say. It doesn't matter. Let's assume that you're speculatively executing this in Runahead mode, and you get to this branch. One of the input values is invalid, so you cannot resolve it. So the branch predictor took you this way. Well, let me use some other color for the branch prediction. So branch predictor took you this way. You're executing this way, this way, this way. Sounds good. But the real path should have been this way, the green one. Okay. So you were on the wrong path clearly for some time. And then you reconverged. So this is the wrong path. You execute it. You don't know, and you cannot know because the branch is invalid. You cannot resolve the branch. So you cannot recover and re-execute from this part. What you did in the wrong path clearly affected what you execute over here because some of these input instructions over here are data dependent on what here. But what you did on the wrong path may be useful also, right? Basically, let's assume that you load some value over here. And let's assume that this part also loads something. And they happen to be the same cache line, right? Cache line A, right? While you're executing on the wrong path here, you loaded cache line A, and you kept executing, maybe cache line B, cache line C, cache line D. And if you executed correctly, you would have needed A, B, C, D anyway, right? So this is one example of why a mispredicted invalid branch doesn't hurt you much, right? Because the wrong path execution is accessing the same cache blocks as the correct path execution. Plus, at some point you would converge. You're not on the wrong path anymore. Yes, some of your data values may not be correct, but all you need is for your cache block addresses that you prefetch to be correct, right? And in this case, it happens to be correct because I just made it up, right? But basically, a lot of our long path analysis found that this is a case that happens. And this is one of the useful cases where a mispredicted invalid branch doesn't hurt your performance. But there are other cases where a mispredicted invalid branch hurts your performance a little bit, but maybe not as much. And there are some other reasons why a mispredicted invalid branch actually leads to good results, good prefetches. Let me put it that way. Actually, one of the other cases of a mispredicted invalid branch, if I can do it, okay. Okay, another screen. Basically, if you have this loop, right? So let's assume that you have a loop iteration. You have a branch over here, and okay, let's assume that you have another branch over here. If branch else . So if you have a mispredicted invalid branch over here, again, so the previous case actually applies to this basically. If you have a mispredicted invalid branch over here, then you're on the correct path again, and you can prefetch for the later loop iterations as well. Now, on the other hand, if this branch is mispredicted and if it's invalid for whatever reason, then the correct path should be maybe this one, and this is the incorrect path. You may be prefetching for future iterations of this loop later on. That's a possibility, and that happens. We've seen that also. Or this may be the correct path, and this may be the incorrect path. In this case, at some point, you're going to fall through the branch anyway, and you may be prefetching for this part. So basically, even though you're mispredicted invalid, at some point, you may get to those parts in the code that you execute. And as long as you prefetch the cache blocks correctly, you can still generate useful prefetches on, let's say, the mispredicted invalid path. Hopefully that clarifies this. Okay, cool. Yeah, so actually we analyze this a lot because it's an important part of Runahead execution. And I'm going to recommend a paper that discusses this somewhere later in this lecture. Okay, so let's get back to sharing my screen over here, if I can find it. Okay, I did find it. Good. Okay, so that covers branch handling in Runahead mode. And that's basically it, basically. I covered most of the things related to Runahead mode. There's, of course, other stuff that you may want to be aware of, but these are the changes that are needed for Runahead execution. You can see Runahead cache over here, which we discussed, and the checkpoint architecture register file, which could be even smaller than what you see over here, and then some invalid bits to keep track of stuff over here. So the overall hardware cost is not very high, as you can see, and this is an execution-based prefetcher. So let me talk about the advantages and disadvantages, and then I'll go into a little bit more detail in Runahead execution. So this actually leads to very accurate prefetches for data and instructions at all cache levels because it follows the program path. Our results in our initial paper show that more than 90%, actually closer to 95% of the prefetches that you generate are accurate, which is a very high accuracy for a prefetcher, as we had seen earlier. If you remember, we had seen accuracies that are close to 0% in some prefetchers. It's simple to implement. Most of the hardware is already built in. And versus other pre-execution-based prefetching mechanisms, as we saw actually, it uses the same thread context as main thread. There's no waste of context, and there's no need to construct a pre-execution thread because the program already did it for you. The pre-execution thread is your main program. You just need to decide what to execute and what to make invalid. Of course, there are disadvantages and limitations. You extra execute instructions, as you mentioned earlier. This leads to power consumption, additional, and as we will discuss that briefly. You're limited by your branch prediction accuracy. As I said, you'd rather be on the correct path as opposed to wrong path, even when wrong path is useful. And at some point, you're limited by branch prediction accuracy. You cannot prefetch dependent cache misses. That's unfortunate. I mean, you could prefetch actually if you jump ahead in the program. There are potential improvements to Runahead that are actually very interesting to investigate going forward, I think. And your effectiveness is limited by available memory level parallelism or how you extract memory level parallelism, because if you don't find useful blocks to prefetch, clearly you have a problem, right? You will not be effective. And prefetch distance, how far ahead to prefetch, is limited by memory latency, because when the original miss returns back, you abandon Runahead execution. Now, there's some freedom you have actually. You could keep going for a while. If you're actually doing this on a separate thread context, you could keep going for a longer while, like IBM Power 6 did. But maybe they didn't do it exactly well, as we will see also in a little bit. So your prefetch distance actually can be increased by changing the answer to where do you execute this Runahead thread. Okay, let me give you some results. This is from our original paper that basically shows that Runahead execution on a state-of-the-art processor buys you significant performance compared to a prefetcher. So this is no prefetcher, no Runahead. This is a bad baseline. But if you put only prefetcher, you get here, blue part. This is a good baseline. Only Runahead actually performs it like this. And if you actually combine Prefetcher and Runahead, you get 22% over the Prefetcher-based baseline. So this is average across more than 140 applications that Intel used to design its processors with. And you can see that there are interesting trade-offs I'm not going to go into over here. In some cases, prefetching is really beneficial. It's better than Runahead. These are actually floating point workloads that are streaming. And this was a stream locality-based prefetcher like what I discussed in the last lecture. If the prefetcher is able to capture the patterns, it's better than Runahead alone. But if you actually implement both of them together, it's better to have both of them together. This is the same conclusion IBM folks have reached in Power 6, actually. They basically said Runahead and Prefetcher are better to implement together because they're synergistic with each other. There's a question over here. Is it useful to apply Runahead execution together with out-of-order execution and or multi-threading in a core? Or are they usually not applied together? So basically, the short answer is yes. It's useful to apply Runahead together with out-of-order execution. As you have seen, this is an out-of-order processor, actually. It's a very aggressive out-of-order processor for its time. And we compared it to even more aggressive out-of-order processors, and Runahead execution outperforms more aggressive out-of-order processors. I deleted that slide from here, but you can watch one of the later lectures. So clearly, yes, with out-of-order execution. And multi-threading also, yes, basically. You could, if you have multi-threading, you could do the Runahead execution on a different separate thread. This will improve your single thread performance, clearly. Okay. And actually, IBM Power 6 did the Runahead execution on a separate thread. They did some other slightly different design choices. But in the end, they reached the same conclusion we reached, which is it's good to apply Runahead and Prefetcher together, and you get a lot more performance that way. Okay, let me give you results with in-order versus out-of-order processors. Again, this is from my dissertation. This is the in-order baseline with prefetching. And if you add Runahead to it, you get significant performance improvement, about 40%, let's say, ballpark. This is the out-of-order baseline with prefetching. You can see that it's much better than in-order. That's why there's a reason why out-of-order processors are out there and they're dominant today. There's a significant performance gap between out-of-order and in-order. And if you add Runahead execution on top of the out-of-order, you get about 20%. So these results are a little bit different from these results because they're on a different setting over here, so that we could we don't penalize the in-order engine as much. Okay, so you can see that this idea is applicable to in-order and out-of-order and Runahead as well. And if you're interested, you can read this short paper, but for some reason, I don't have the long paper, but I'm going to add it later on. So Runahead was implemented in Sun Rock, and you can see this is a paper that I would recommend. You can see that these folks they called it hardware scouting. They said that it increased the performance of an already robust core by up to 40% for commercial benchmarks, and they implemented on in-order processor. So their results are actually very similar to what we have shown. You get about 40% on top of in-order processors. And if you're really interested in where these folks have taken Runahead after they implemented it, they actually did even more than Runahead. They actually tried to so Runahead clearly generates some results, and they actually tried to reuse those results without discarding them, right? Runahead, we made the choice to discard those results because we thought it was too complicated and you didn't get a lot of benefits from those results. And I still think it's too complicated, frankly, to incorporate those results. And if you read this paper, maybe you will share my view. The paper actually proposed a complicated architecture that can do Runahead, but on top of Runahead, it can actually reuse the results, and it actually can launch this, what is called simultaneous speculative threading, which does Runahead, non-Runahead at the same time. It's very interesting, but it's a bit complex also. So you can do better than Runahead, basically. And I'd also recommend this paper that looks at comparing Runahead execution versus conventional data prefetching in IBM Power 6 in real implementation of IBM Power 6. And I'm not going to go into the detail, but basically, they basically say that you get a better benefit by using Runahead and prefetching at the same time. And there's more analysis in the paper. Okay, so let me talk about Runahead enhancements a little bit, because this addresses some of the issues with speculative execution-based prefetching. And these are some papers that I would recommend. This wrong path event paper actually tries to get rid of, tries to find out whether you're on the wrong path without knowing that you're on the wrong path. Can you actually use some hints from what's happening in the processor to actually predict that you're on the wrong path? And we identified three major limitations of the Runahead mechanism, baseline Runahead mechanism. One is, as one of you pointed out, energy inefficiency. You execute a large number of instructions speculatively, and we provided some solutions to this. And I think in the end, you really want to use solutions like this to employ Runahead execution in the field. The second part is it's ineffective for pointer-intensive applications because you cannot parallelize dependent cache misses clearly, because if a cache miss is dependent on an L2 cache miss, then you get an invalid value as input to the second cache miss, and you cannot even see the address of it, right? And you can predict the first cache miss's value to solve this. And this idea actually works in many cases, as we will discuss very briefly. And then as we discussed, there are mispredicted invalid branches or irresolvable branch misprediction in Runahead mode. You cannot recover from a mispredicted and invalid branch. And this paper attempts to actually solve that problem, basically. Somehow identify events in the processor that are abnormal, let's say, or irregular. And it uses them as hints that you're on the wrong path. For example, if you're dereferencing a 0 pointer, null pointer, it's likely that you're on the wrong path or your program is correct. And I'd rather take the likelihood that I'm on the wrong path and say that I made a mistake somewhere. If your program is incorrect, then you have a problem to begin with anyway, right? You don't care how much you accelerate your program. Okay, so let's take a look at the efficiency problem very quickly, because this exists in all of the thread-based prefetching mechanisms. And this is in particular to Runahead. And these are some workloads, as you can see. This is average. Basically, what we're looking at is the percentage increase in performance in single thread and percentage increase in executed instructions. So on average, it doesn't look terrible. On average, Runahead execution increases the IPC by 22%, but increases the executed instructions by 27%. So if you do the ballpark that an increase in executed instruction, a 1 unit increase in executed instruction is a 1 unit increase in energy, then you can say, okay, this is not terrible in terms of energy efficiency. But some workloads are terrible. Basically, in this workload, you increase IPC very little, but you increase executed instructions by almost 60%. On this workload, you actually lose performance just a little bit. It's not seen here because the loss is very little, but increased in executed instructions is about 50%. On this workload, where you're very good, actually, you increase IPC a lot, but you increase executed instructions also a lot. So the key question is, can we actually get a similar increase in IPC performance while limiting the increase in executed instructions? And the answer is yes, basically. And it's really described in these papers that talk about how to make Runahead execution more efficient. And there are multiple causes of inefficiency that I will briefly talk about. And you will hopefully empathize with the causes of inefficiency, because whenever you design a thread-based pre-execution system, you'll really need to deal with these issues. And one is short Runahead periods, overlapping Runahead periods, and useless Runahead periods. Let me give you pictorially what these things are. I'm not going to go into detail of how we solve the problem, but you can imagine solutions once you know what the problem is. So basically, short Runahead periods are Runahead periods where you're in Runahead mode for a very short time, usually due to an already in-flight L2 miss generated by the prefetcher, wrong path, or a previous Runahead period. So it looks like this. You get a long latency cache miss. You think long latency cache miss. You enter Runahead mode, and the cache miss, well, sorry, this is not what I wanted to say, actually. This is what you, okay, this is the second one. Yeah, this is Runahead mode. This is an example. This is a good Runahead mode, let's say. This is what should happen. You get a long latency cache miss, and while you're pre-executing, you get another long latency cache miss. You parallelize things, and then you exit Runahead mode when the first cache miss comes back that put you into the Runahead mode. And you re-execute the load, and you get a load hit. And while you're executing in normal mode, the second miss didn't complete yet, but you reach the miss, and you enter Runahead mode again. Well, that doesn't sound good because the miss is going to complete very soon. So the second Runahead period is short Runahead period. Clearly, you could have avoided it, right? If you actually kept track of how long this miss has been outstanding, right? And you could have avoided it easily. But original Runahead doesn't avoid it. As a result, it leads to these short periods, and they're clearly less likely to generate useful L2 misses because you're not running ahead much. You're not pre-executing far ahead. And they have high overhead due to the flush penalty, which is the red part over here at Runahead exit. So you would like to avoid these as much as possible. And I just gave you a mechanism to avoid it. Basically, keep track of how long the miss has been outstanding. If it has been outstanding for a long time, guess that you should not enter Runahead mode because it'll be a short Runahead period. Okay, that's the idea. The second period is a bit different. The second type of period that leads to inefficiency is a little bit different. It's called overlapping run-ahead periods. And these are two run-ahead periods that execute the same instructions. So let's take a look at an example. So again, this is a run-ahead period. You get a load miss. The second load is dependent. You get a load to invalid. So you cannot parallelize. That's not good. In the end, you flush the pipeline without run-ahead being beneficial. But on top of that, after you exit run-ahead mode, you re-execute this load 2. Now you have the data value because load 1 is completed, right? And the second load was dependent. Now you enter run-ahead mode again with that load 2 miss. Now what happened is you have an overlap of instructions that you execute in 2 run-ahead modes. Now, this run-ahead mode was useless in this particular case, but this run-ahead mode doesn't need to be useless. There may be another load 3 miss that you could enable because this load 1 hit now, right? So this overlap is not necessarily useless, but what we found is that a lot of the overlap is very inefficient. So we try to eliminate the overlap as much as possible. And you can imagine how to eliminate that overlap. You can read the paper for more detail. It's relatively simple techniques to eliminate these things. And finally, there are purely useless run-ahead periods that are not short, not overlapping. These are run-ahead periods that do not result in prefetches for normal loads for whatever reason, usually because we don't have enough memory level parallelism to reach the next load instruction that leads to a cache miss over here. Or you didn't do a good job in your run-ahead. You didn't really do, you were not aggressive enough. Either your prefetch distance was limited, or you were not aggressive enough to go far ahead and run ahead, right? Or fundamentally, you don't have enough parallelism in your workload, parallelism in the sense that memory level parallelism, to get to the next miss early enough. So there are multiple reasons why these exist, actually, but in the end, they could all boil down to either the lack of memory level parallelism or the lack of the ability to exploit that memory level parallelism that may otherwise exist. So we basically eliminate these also, and we use a prediction mechanism to predict if a period will generate useful L2 misses. And you can read actually the paper. It's a simple, very simple prediction mechanism. Okay, so if you do all of those, and these are cool techniques, I think. This paper also says you should drop the floating point instructions in run-ahead mode so that you could get to the next cache miss. And I think, I don't remember actually if this figure includes those techniques. I believe it doesn't because that's a separate technique. But basically, you could reduce the execute instructions from about 27% to 6%, which is a huge improvement in the extra instructions that you execute in run-ahead mode, while preserving the benefits in terms of performance. So the performance benefits go from 22.6 to 22.1. So this is clearly a much better trade-off, right? You get 4x smaller execute instructions, and overall you increase your execute instructions by 6%, while increasing your performance by 22%. So that's what I mean by you should really design your prefetching engine very carefully if you're doing pre-execution based prefetching. I mean, that's true for any kind of prefetching actually, but pre-execution based prefetching is even more important because you may be competing with the main thread, right, in this case. Okay, so if you would like to know more about efficient run-ahead execution, you can take a look at this paper, and this is the shorter version of it. So let me quickly talk about the pointer intensive application part also. Dependent cache misses are actually, I've already shown you this picture, but dependent cache misses, these are pointer-based data structure, basically. If load 2 is dependent on load 1, in run-ahead mode, you get an invalid in load 2 because you cannot compute load 2's address. Clearly, you cannot prefetch it, right? That's not good. On top of that, it causes inefficiency because when you exit run-ahead mode, you re-enter run-ahead mode again if this load 2 is a cache miss. Right? So it causes an overlapping run-ahead period. So a much better way of handling this is actually predicting the value of this load, as we will see. But basically, run-ahead execution cannot parallelize dependent cache misses. It leads to wasted opportunity to improve performance and wasted energy because of useless pre-execution. And we actually did ideal studies. If you have a good simulator, you can actually do ideal studies where you ideally know the address of the load and you don't do what I showed you in this picture. And the performance would improve by 25% if this limitation were ideally overcome. And we get reasonably close to this 25% with the technique that I'm going to describe. Basically, the idea is to predict enable the parallelization of dependent L2 cache misses in run-ahead mode with a low-cost mechanism by predicting the values of L2 miss address loads, meaning pointer loads. So you get into the situation only when you're pointer chasing. So you identify which loads are pointer loads, and you predict their address, their values. That's the idea. So address load is a load that loads an address into its destination register, which is later used to calculate the address of another load. And you can figure out what's an address load with techniques. You've seen one technique in content-directed prefetching, as we discussed last time. As a contrast this to a data load whose result will not be used as an address or to calculate an address, basically. And if you really want to know how to do this, I'm going to refer you to this paper that we wrote in 2005. But basic idea is to have a very specialized prediction mechanism for load 2's address or load 1's value, such that load 2 can compute its address now reasonably accurately so that you can generate a cache miss that goes to the correct cache block. And then when you're in Runahead mode, that load 2 hits. So you're back to, let's say, business in Runahead execution because you can parallelize the second load that you could otherwise not parallelize. And the idea is to really, using a specialized mechanism, value predict this first load miss. I'm not going to go into the details of it because that would be too much, I think. But if you're really interested, I think it's a cool mechanism, a very simple mechanism to predict in special cases the value that's generated by this load 1 that's going to be used as an address or that's going to be used in the calculation of the address for load 2. And you save speculative instructions as well, clearly, by doing this. Okay, and this paper proposes it, and there's a longer version of it that looks at how to do it in more detail. We actually look at some software changes to enable this hardware technique to be much more effective as well in this longer version of this work. Okay, so if you want to know more about Runahead execution, there's a longer video in the 2017 incarnation of this course. I've given you a shorter version of that. The longer version of that goes into long comparisons of Runahead execution to out-of-order execution, for example, which I believe is really interesting and goes into more results if you're interested. But we don't have time in this semester to cover that. And you can certainly read my dissertation, which covers a lot more than the papers actually cover on this topic. Okay, any questions on this or anything else we've covered? Okay, if not, I'm going to continue. Basically, I wanted to cover this because this is an execution-based prefetcher in the end. So Runahead execution is one of the simplest execution-based prefetchers that you can build that is proposed so far as I know. It's an execution-based prefetcher. It clearly makes trade-offs different from the software-controlled pre-execution that we discussed, right? You don't need an SMT thread, for example. But basically, recall the idea of an execution-based prefetcher. We want to pre-execute a piece of the prune program solely for prefetching data. And the idea of Runahead is pre-execute the main program solely for prefetching data. So it's no different, except you make your life easy by not creating a different piece of the program. And clearly, I'm not going to go into the details of this, but you can think about advantages and disadvantages of Runahead versus other execution-based prefetchers that we've discussed or that you may read about. And there's a good question over here, which is, can you make Runahead even better by pruning the program portion executed in Runahead mode? So for example, I mentioned the dropping of floating point instructions. That's one example of pruning. You can also try to be even more intelligent and try to get rid of all instructions that you don't think are going to contribute to L2 cache misses. You need to be careful, of course. You also don't want to eliminate instructions that are important for your control flow. You don't want to increase the probability of mispredicted invalid branches while pruning your program, clearly, right? So basically, these all point to taking advantage of pure speculation. Runahead mode and an execution-based prefetcher is purely speculative. The goal is to find and generate cache misses that would otherwise stall execution later on. And the key question, I think, and a key research question going into the future that I do not believe is answered very well is, how do we achieve this goal most efficiently and with the highest benefit? So there's more to do, in my opinion, in this area. And I think one seed of ideas, to find and execute only those instructions that will lead to cache misses. Clearly, that cannot already be captured by the instruction window of the processor. And the key question is how. And I may have some ideas, but I don't have the answers related to this. But if anybody has interest on this topic, this is certainly an important topic going into the future, because Runahead continues to attract a lot of interest from industry to simplify, to get higher performance in a single thread, but also at the same time simplify the designs of the systems. Because increasing the size of the instruction window is actually not so easy as you may think. Even though Apple increasing the size of the instruction window, we don't exactly know how they did it, for example, right? Okay, so let's talk about execution-based prefetchers. There are some pros and cons. This is going to be somewhat similar to Runahead execution, but I'm going to be more general over here. Basically, an execution-based prefetcher can pretty much prefetch any access pattern. Runahead, for example, can prefetch. It's better than a hardware prefetcher, as we showed. IBM folks showed exactly the opposite, basically. They said that Runahead is worse than their hardware-based prefetcher, but when they're combined together, they're better than either of those alone. It depends on how you implement Runahead, of course. Maybe they didn't employ some of the sophisticated techniques we employed, but you can prefetch pretty much any access pattern. And it can be very low cost, like Runahead execution. And this is especially true if you use the same hardware context. And the reason is the processor is equipped to execute the program anyway. But also, even if you use some other context, some other core, it can be relatively low cost because the system is equipped to execute the program anyway. I also realized that there's 3 S's over here. So I'm going to fix these slides since they're unfortunate. I'm going to fix this one right now. Oh, okay. I don't know what happened here. So as I exit, why does sharing get stopped? Sorry about that. There are some idiosyncrasies in Zoom that you don't expect normally. Okay, let me share again. Okay, there you go. Now processor is fixed. Okay, and you can be bandwidth efficient actually. If you control execution-based prefetching really well, you can be very bandwidth efficient. And Runahead execution is actually very, very bandwidth efficient. You can see in the papers that it doesn't increase the bandwidth consumption much. You don't need a lot of bandwidth to do Runahead execution. But of course, any execution-based prefetcher is dependent on branch prediction and possibly value prediction accuracy. Mispredicted branches depend on missing data, throw the thread off the correct execution path. This is true for software-controlled pre-execution as well. In some of those executions, you can see that they actually get rid of branch calculations so that they can save time. And if you mispredict, at that point, you're doing something, I'm not going to say wrong, but you may not be getting as much benefit, right? You may not be on the correct path. So that's true for not just Runahead, but all of the execution-based prefetchers. It can be wasteful, as you have seen, observed. You can speculatively execute many instructions. As a result, it can be energy inefficient, power inefficient. If you use some other thread context, you can be even more power inefficient. And if you actually flush the pipeline like we do, you can be even more power inefficient, right? So there are multiple reasons why you can be wasteful. And you can occupy a separate thread context as we discussed. And there's some complexity in deciding when and what to pre-execute. These questions actually are still important to examine, and the answers to them are not perfectly clear in many thread-based, execution-based prefetchers. Okay. So with that, I think let me very quickly cover some multi-core issues. I'm not going to go into detail in multi-core issues, but I can recommend you some past lectures potentially on this one. But in multi-core, basically, everything we said becomes exacerbated. Prefetching is still important to improve the performance of single thread. But if you do something wrong in prefetching, you may actually cause a lot of issues. So for example, prefetching shared data could be very beneficial. You can reduce coherence. This is this way. We're going to talk about coherence early next week. So this is going to be interesting. So there's another application of prefetching in multi-core or multi-processors, let's say. You can prefetch a block that is written by some other thread, for example. But if you do prefetching wrong, you may actually cause some issues related to coherence as well, right? As I said, prefetch efficiency is a lot more important because bus bandwidth is much more precious and cache space is very valuable. So you need to be very, very careful. And one core's prefetches interfere with other cores' requests, as well as other cores' prefetches. You can have more cache conflicts, more bus contention, and more DRAM bank and row buffer contention because of prefetches, even accurate prefetches. So in fact, in some of our works, we showed that even if your prefetcher is accurate, if it's aggressive, it can destroy the performance of some other core because it's basically evicting useful demand requests from the caches that are shared or delaying the requests, useful demand requests of some other core in the DRAM banks and row buffer. So you need to be even more careful and you need to incorporate prefetchers into your quality of service mechanisms and interference control mechanisms that we discussed in the memory interference and quality of service lectures. So there are 2 key issues over here 2 key other issues that I will very briefly discuss. One is how to prioritize prefetches versus demands of the same core and of different cores. This becomes important. And the second is how to control the aggressiveness of multiple prefetches to achieve high overall performance. And the finding that we have is you need to coordinate the actions of independent prefetchers for best system performance. Each prefetcher has its different accuracy, coverage, timeliness, bandwidth demand, interference it's causing, etc. If you coordinate the actions of independent prefetchers, you get much better system performance as opposed to letting them run wild, right? And potentially destroy different programs' performance. And there are some examples in literature that I'm not going to go into the details. I mean, we covered the feedback-directed prefetching. You need to control prefetcher aggressiveness like that. But feedback-directed prefetching as proposed doesn't work because it doesn't coordinate the actions of different prefetchers clearly, right? It looks at a single core prefetcher. So the later work looks at coordinating the control of multiple prefetchers in an intelligent way. And I think this is very interesting. How do you prioritize prefetches versus demands from cores? There are prefetch-aware memory controllers and shared resource management. This is also very interesting. And we already talked about bandwidth efficient prefetching of different data structures. Again, I'm not going to go through the details, but these are a bunch of works. If you're interested, you can take a look. This is a coordinated control work that's important, I think, in multi-core. And this paper actually has a really good insight, which is sometimes you don't want to deprioritize prefetches always, basically. Sometimes you want to prioritize prefetches as well as the demands if the prefetcher is doing well. And because you want to exploit the row buffer locality in the system. So this paper proposed an adaptive mechanism to decide how to prioritize prefetches versus demands. And there are a bunch of other interesting issues with prefetching. Basically, prefetching complicates a lot of issues that we discussed in the memory system. So far, we kind of discussed the memory system as if prefetching doesn't exist. But that's not true, clearly. Prefetching is a first-class component of all systems today. So you cannot ignore how to handle prefetches in the memory system. And this is, I think these works actually complete the story for you, but clearly we don't have time to go over those. So I will refer you to these works. And these are some of the more recent works that we discussed. And clearly prefetching can be done in GPUs as well, but you need to be even more careful in GPUs. Why? Because you have a lot of parallelism in GPUs, a lot of bandwidth, but you also have a lot of bandwidth demand. So you need to schedule your prefetches and coordinate it with different scheduling mechanisms that you have in the GPUs that I definitely am not going to talk about over here, but this is a fascinating topic as well. Okay, so that brings me to the end of the first part of the lecture. So this is a good time to, I think, take a break. Unless there are questions, I will wait for some time for questions. And then we're going to take a break until, let's say 14:50, about 14 minutes again. Okay. So I guess I don't see any questions. People ask very good questions, I think, early on. That's good. Keep them coming. So let's take a break, and then we will start at 14:50 with the multiprocessors.